All right, section 11.6, absolute convergence and the ratio and root tests. They're a little bit different in this section. I mean, we're still talking about tests that can be used to determine convergence or divergence of a series, but it'll be a little bit different approach in this section. You know, what is this absolute convergence and what is that all about? And then the two tests that we're going to talk about, primarily it's going to be the ratio test. The root test, we'll mention that one. That's not going to be a big player, but we'll at least show you how that one can be used. All right, so given a series, sum of a sub n, if we consider the corresponding series of its absolute values, right? So we've talked about that before, where I just look at the absolute values of the terms. So our sum is of the absolute value of a sub n. So absolute value of a sub 1, absolute value of a sub 2, etc., etc. So where the terms are the absolute values of the terms of that original series. Definition: a series a sub n is called absolutely convergent if the series of absolute values is convergent. All right. So if we check the series of the absolute values and we show that that series is convergent, then we can say that the original series is absolutely convergent. So for example, if I take the sum as n goes from 1 to infinity of negative 1 to the n over n to the fourth, right? Looking at the first few terms of that series, so for n equals 1, I've got negative 1. For n equals 2, 1 over 2 to the fourth positive, right? And there's our negative 1 to the n. We've talked about it's going to alternate the signs of those terms. So plus 1 over 2 to the fourth, minus 1 over 3 to the fourth, etc., etc. And then if we look at the absolute values of those terms, right? So the sum as n goes from 1 to infinity of the absolute value of negative 1 to the n over n to the fourth. So I can drop the negative 1 because the absolute value is going to turn everything positive. And so I'm looking at the terms of that series, 1 over n to the fourth, 1 plus, that'd be 1 over 2 to the fourth, or 1/16, 1 over 3 to the fourth, or 1 over 81. But regardless, you should recognize that the sum of 1 over n to the fourth, that's a p series. Right? That's one of our 1 over n to the p. With p equal to 4, which we know is a convergent series. Right? So I can say then that since this series, sum as n goes from 1 to infinity of 1 over n to the fourth, is a convergent series, and that series is formed from the absolute value of the original series, then I could say that this original series is absolutely convergent. Right? That's the comparison. That's the test, or what you're determining here. Right? So I'm looking at what does it mean to be absolutely convergent. It means that the absolute value of the terms of my series, or the absolute value of my series, is convergent, which then makes my series absolutely convergent. So that's what that means. For example, consider the sum that goes from 1 to infinity of negative 1 to the n minus 1 over n. Right? And so again, there's our negative 1 to a power. And then we said we could play with that index. If we wanted the first term to be positive or negative, you can use n or n minus 1, whichever is appropriate. But in this case, with negative 1 to the n minus 1, when I start at n equals 1, then that would give me negative 1 to the 0 power, which is 1, right, over 1. So I get positive 1 for the first term. And then we're alternating positive, negative from there. Right? So minus a half, plus a third, minus a fourth, etc., etc. We know that that series is convergent. If we look at the alternating series test, right, that's a perfect example of an alternating series, right? The terms are alternating sign. The absolute values are decreasing, right? 1 half, 1/3, 1/4, etc. And the limit as n approaches infinity of the absolute value, 1 over n, is 0. And that's classic alternating series test. But if you look at the sum of the absolute value of that series, right, so the absolute value of negative 1 over n to the n minus 1 over n, that's going to give us the sum as n goes from 1 to infinity of 1 over n. And I can drop the negative 1 because of the absolute value. But we know that that series is divergent. That's our harmonic series, and that's our p series with p equal 1. We said that was a kind of a special series. It's our harmonic series. But we know that the divergent series. So what have we seen in this case? The sum as n goes from 1 to infinity of negative 1 to the n minus 1 over n is a convergent series. We prove that, or can show that, using alternating series test. but recognize that this is not an absolutely convergent series, right? So there's two different things that you're talking about there. And I know sometimes it can be a little misleading or maybe a little confusing as far as what does absolutely convergent actually mean. All right, so remember, absolutely convergent means that you're looking at the series or the sum of the absolute values of your series. And if that is convergent, that's what we're calling absolutely convergent because it's converging absolute values. Maybe that would make a little more sense. So at the bottom, then we have a definition. We say that the series A sub n is called conditionally convergent if it is a convergent series that is not absolutely convergent. All right, so that's that example that we just did. That's a convergent series that is not absolutely convergent, so we call that conditionally convergent. Then we have our theorem at the bottom, and this is a pretty important theorem because this is actually kind of the basis of the whole reasoning behind this observation about absolute convergence. If a series A sub n is absolutely convergent, then it is also convergent. All right, and since this is what we are primarily interested in, whether or not the series is convergent or not, then here's another way that I could possibly determine convergence. If I can show that a series is absolutely convergent, then I can also take it to be convergent. Now again, the converse is not necessarily true, right? Right above that, if I have a series that's convergent, does not necessarily mean that it is absolutely convergent. But if it is absolutely convergent, this theorem tells us that it is indeed convergent. Right? And again, this is ultimately what we're interested in. We're trying to determine still whether the series is convergent or not. So this is going to give us another test that we can use for convergence. If I can show absolute convergence, then I have convergence. For example, now let's consider this series. Sum as n goes from 1 to infinity, the sine of 4n over 4 to the n. And I've listed out the first few terms of that series: sine of 4 over 4, sine of 8 over 16, sine of 12 over 64, etc., for n equals 1, 2, 3, and so forth. And then I also gave some approximations to those, right, to give us an idea of what the terms of that series look like. But notice, we do have some positive terms there. We do have negative terms there, but they're not alternating, right? So like an alternating series test wouldn't fit here because even though we do have positive and negative terms, they're not alternating sign, right? It's negative, positive, then it's negative, but then it's negative again. Right, so alternating series doesn't apply. But if we look at the absolute value of this series, right? So the sum as n goes from 1 to infinity of the absolute value of sine of 4n over 4 to the n. Now, here's a statement that we know to be true. We've made this observation before, right? And so you kind of have to watch for situations like this where, okay, especially with these trig functions, we know that the value of the sine function has to be less than or equal to 1. Right? Sine always falls between -1 and 1, so its absolute value has to be less than or equal to 1. I don't care what the argument is. This is always a true statement. So then we can bring in our comparison test. And I can say then, all right, if I look at the absolute value of the sine of 4n over 4n, I know that that has to be less than or equal to 1 over 4n, because sine of 4n is less than 1, right, from that comparison above. So we know this statement to be true as far as a comparison between those series. So then if I look at the sum as n goes from 1 to infinity of 1 over 4n, recognize that's a geometric series. Right? We've talked about those extensively. When I see a constant to the nth power, I think geometric series. Furthermore, we know that it's a convergent geometric series because our r in this case is 1/4. So the sum of 1 over 4 to the n is a convergent geometric series. We know that the sum of the absolute values of the terms of our series is smaller than that. And with our comparison test, that's a perfect comparison, because if I can show that my terms are smaller than a convergent series, then my series has to converge. Now, the series we're saying is convergent is this one, is this absolute value. So then what does it mean that I've found? I have found that that sum of the absolute value is convergent not absolute, absolute values is what I want to put there. Right? So that's the sum of the absolute values, which is convergent, which means that the original series is absolutely convergent. Right? And since that original series is absolutely convergent, we can also say then that it is convergent. And that's what I'm interested in. That's what I want to determine ultimately, whether I have a convergent series or not. Okay? Now, this comparison test with absolute value, again, it's like any of these other tests. I mean, we keep talking about using an appropriate test or recognizing what type of test is going to work. Well, in this case, I could make a comparison, and it was all based upon what we knew about sine of 4n. Right? Because we knew the sine of 4n is going to be less than or equal to 1. That's what set up the comparison. And then looking at the absolute value, showing that the absolute value converges, which means the series is absolutely convergent and therefore convergent. Right? Now, helpful tests for determining absolute convergence. This ratio test that I mentioned at the beginning. This is a big player. This is a big deal. You're going to see ratio tests used quite a bit in determining absolute convergence. Now, again, it's going to be one of those tests like any of the other tests. There is no magic pill, so it's not a test that I can use all the time. Like anything else, you have to be careful of, first of all, how to use it. Secondly, how to interpret the results. And that's, I find, is the biggest issue with the ratio test, because it's easy to confuse the ratio test, or at least the results of it, with that limit comparison test that we looked at previously. So here's what ratio test tells us. If the limit is n approaches infinity of the ratio of a sub n plus 1 over a sub n, the absolute value, is equal to some number L less than 1, then the series a sub n, the original series, is absolutely convergent and therefore convergent. Right? So what am I looking at? I'm looking at the ratio of the terms of my series and the next term of the series. Right? So our a sub n, our generic nth term, and the a sub n plus 1 term. What's the next term in the series? So then I look at the absolute value of their ratio. If that is equal to some number L less than 1, then we're saying that the original series is absolutely convergent, which then we said that guarantees us convergence. Part 2 of this, limit as n approaches infinity, absolute value of a sub n plus 1 over a sub n, in this case equal to L but greater than 1, or if that limit is infinity, then the series is divergent. Okay? So it's all about, first of all, does the limit exist? If it exists, is the value greater than 1 or less than 1? If it's less than 1, it's convergent, or more precisely, absolute convergent, which makes it convergent. Or if it's greater than 1, then it's divergent. We also have, if that limit is infinity, we have a divergent series as well. And the proof of this, or if you look at the reason why this works, it has to do with geometric series. We said for geometric series, if r is between -1 and 1, or if the absolute value of r is less than 1, we have a convergent geometric series. And if the absolute value is greater than or equal to 1, it's divergent. Now in this case, less than is convergent, greater than is divergent. But there is a third part. And so that's kind of where this one is based upon. So maybe keep that in mind. It's very much related to what happens with geometric series. But there is one difference. Look at number 3. If that limit as n approaches infinity of a sub n over a sub n plus 1 over a sub n absolute value is equal to L, which is equal to 1, then this test is inconclusive. So in other words, we can't use it. All right? So if the limit exists and is equal to 1, then this test tells us nothing about convergence or divergence of our series. It tells us nothing about absolute convergence of the series. And so as a result, we have to use some other tests. Right? So it's kind of like that test for divergence that we started out, that test that said if I look at the limit as n approaches infinity of a sub n, right, the terms of my series, we know that in order for the series to be convergent, that limit has to equal 0. But we said if that limit was not 0, we knew that the series automatically was divergent. That was our test for divergence. But if the limit is 0, we know that has to happen for convergence to happen, but just because that happens doesn't necessarily mean the series was convergent. So that's what led to all these other tests that we're looking at. What happens if that limit is n approaching the infinity of a sub n is 0? Right? I can't say necessarily the series is convergent. It may or may not be. Right? So again, it's inconclusive in that case. Right? So it's kind of along those lines. So be careful with this ratio test. Right? So ratio equal to 1 is inconclusive. And I'll show you an example of that. I'll show you how that works here in just a minute. All right, so let's say, for example, now you're going to start to see maybe some more intricate series here. Right? So as these series get a little bit more involved, this ratio test is really a handy series. It's really a useful series for helping with these more complex types of series. And when you have kind of like these combinations of different things, like notice in the first example I have, the sum as n goes from 1 to infinity of -1 to the n times n squared over 2 to the n, right? We've got a kind of a combination of different things there. We've got the n squared, we got 2 to the n, the -1 to the n, again, that's kind of that alternating series idea. But if we apply the ratio test to this, right, so you may kind of catch on to a little bit of a shortcut here. We'll see. So ratio test says, and now what is the ratio test used for? The ratio test is used to determine absolute convergence. Right? And if I have absolute convergence, then I get convergence. So I look at the limit as n approaches infinity of a sub n plus 1 over a sub n. So what is a sub n plus 1? Well, a sub n plus 1 is exactly that. It's the n plus 1 term of your series. So I'm plugging n plus 1 into our series. So I get -1 to the n plus 1 over n plus, or times n plus 1 squared over 2 to the n plus 1. So this is a sub n plus 1 divided by a sub n, right, which is the series, or the nth term of your series. And then we're taking the absolute value of that. Now, the absolute value knocks out the negative ones, right? So I don't care about the -1 to the n minus 1, or -1 to the n plus 1, -1 to the n. I don't care about that. Absolute value is going to make everything positive. Notice, too, then, all I'm going to do is, since I'm dividing by a fraction, I'm just going to multiply by the reciprocal. Now, you'll see that happen quite often with these series that we apply ratio tests to. Quite often they are rational functions, or rational expressions. So dividing by the fraction, multiply by the reciprocal. You can save yourself a step there. So that leads us to the limit as n approaches infinity of n plus 1 squared over 2 to the n plus 1 times 2 to the n over n squared. Right, so we just got rid of the negative ones, and then we multiplied by the reciprocal. So then the next step, so that gets me here. I've got the limit then as n approaches infinity. Now all I did in this next step was rearrange the factors a little bit. So I took the n plus 1 squared and the n squared and made one fraction out of that. And then I took the 2 to the n and the 2 to the n plus 1 and made one fraction out of that. So that's just rearranging the factors, and that's for convenience sake, just to make it a little clearer as far as the simplification. Now that leads us to the next statement, which said that this is equal to the limit as n approaches infinity of 1/2 times n plus 1 squared over n squared. Now where did all that come from? Well, first of all, notice over here to the left, 2 to the n plus 1 power. That's equal to 2 to the nth power times 2. All right. If I pull off one of the 2's, I'm left with 2 to the nth power. So 2 to the n plus 1 is equal to 2 to the n times 2. And then I took the n plus 1 squared over n squared and just combined that all under one exponent, right? That's our basic rule of exponents. N plus 1 over n all squared. And then with 2 to the n plus 1 being equal to 2 to the n times 2, we could divide out that 2 to the n, leaving us with 2. Let me maybe write that over here on the side, because I don't like the way that looks. So this is what I'm looking at here. This 2 to the n over 2 to the n plus 1 would be equal to 2 to the n over 2 to the n times 2. All right, so that's just rewriting it like we had over here. So that way you can divide out the 2 to the n. That's where that 1/2 comes from. All right. All right, yeah, because that looked a little funky. Maybe skipped an extra too many steps in there. So that gives us the limit as n approaches infinity of 1/2 times n plus 1 over n squared. Now, the n plus 1 over n squared, we can treat that like we always have. You know, we're looking at a limit as n approaches infinity. So let's just do what we normally do with this thing, divide everything by n, and that would give us 1 plus 1 over n over 1. And as n approaches infinity, right, that goes to 0, and we're left with 1 times 1/2, which is 1/2. And that would be the value of that limit, right? But still, ultimately, I mean, once you set up the limit and once you plug everything in, it's really all about evaluating the limit. We keep coming back to that. You know, that's why limits were so important and why we have to, you know, be able to evaluate those guys, because they're used in so many different places. So it's all about evaluating the limit and kind of the tricks and tools that we use to rewrite those things and simplify it. But ultimately, this is what we get as a value for the limit. And since that limit is equal to a constant, 1/2, which is less than 1, then that means that the series is absolutely convergent, right? Because that tells me that I have convergence of the absolute values. Now, since the series is absolutely convergent, then it is also convergent. So I'm going to say that the sum as n goes from 1 to infinity, -1 to the n squared over 2 to the n, is absolutely convergent and therefore convergent. All right, so if we need, and you'll be asked both. I mean, you'll be asked to determine whether the series is absolutely convergent or not, or it just may be a simple question of, is the series convergent? And I can use the absolute convergence to show that with the ratio test. All right, let me do that next example that I have. The sum as n goes from 1 to infinity of n squared over n factorial. I think we had mentioned n factorial before we got done with all this stuff. So let me remind you first of that. So let me go over to the side and do this one. N squared over n factorial. Sum as n goes from 1 to infinity over n factorial. Now, first of all, let's do a little recall here. Remind me about n factorial. I think we mentioned that one in class before we got sent to isolation. All right, what does n factorial mean? It means I'm multiplying 1 times 2 times 3 times 4 times 5 until I hit n. Or if we do that in reverse, how about I multiply n times n minus 1 times n minus 2, right? We just decrease by 1 until we get down to 1. That's n factorial. All right? Almost a given that when you have a series involving these factorials, ratio test is going to be the test of choice, so that you can try to determine or attempt to determine absolute convergence. Right? So it's one of those kind of tip off said, hey, I see a factorial, ratio test is probably going to be my test of choice. All right, so now what am I doing? I'm using ratio tests. So like we always say with these, you got to identify what test you're using, or at least when you're done, what test did you use to make the determination. So I'm using ratio test that says I can then look at the limit as it approaches infinity of the absolute value of a sub n plus 1, which would be n plus 1 squared over n plus 1 factorial over a sub n, which is n squared over n factorial. Right? Now again, we always said it's a sub n plus 1 divided by a sub n. So again, I'm just going to rewrite multiplying by the reciprocal. Now here again, I can drop the absolute values. I don't even have any negatives in there at all, so the absolute value here is not even necessary or not critical. But I do have then the limit as n approaches infinity, so let's drop the absolute value. We'll go ahead and multiply by the reciprocal. So I've got n plus 1 squared over n plus 1 factorial times our reciprocal n factorial over n squared. Okay. Now, let me ask you this first before I go to my next step. Let's go back down here to our factorial. If n factorial is n times n minus 1 times n minus 2, all the way down to 1, what's n plus 1 factorial? Well, that's going to start with n plus 1. And then if we decrease by 1, what do we have? We have n. Decrease by 1, right? Decrease by 1, etc., etc. So it's n plus 1 times n minus 1 times n minus 2, until you get to 1. Or in other words, notice that this is what? This is n plus 1. What's this? That's n factorial, right? So n plus 1 factorial can be written as the product of n plus 1 times n factorial, right? Because all you're doing is multiplying in that extra term. So when I come up here then, right, we're multiplying, there's that n plus 1 factorial. Let's maybe rewrite that as n plus 1 times n factorial. And notice then I would be able to divide out the n factorial. Now I'm going to go ahead and play the little game I played with the previous one. Let's just rearrange those factors. I mean, this is really done for convenience sake more than anything else, just because it looks a little nicer. So I'm going to put the n plus 1 squared over n squared. And then I'm going to rewrite with the n factorial over n plus 1 factorial. All right, and again, like I said, that's really just for convenience. That's just to make it look a little nicer, make it easier to keep track of those things. But, I mean, it's not absolutely necessary that you do that. Now, the n plus 1 squared over n squared, we're going to do like we did before. I can just go ahead and combine those as a fraction, n plus 1 over n all squared, using our rule of exponents. And then the n factorial over n plus 1 factorial, I'm going to rewrite the n plus 1 factorial as n plus 1 times n factorial. All right, so here's rewriting of the n plus 1 over n all squared, rule of exponents. And then we've got the n factorial over, bounce back and forth here, n plus 1 times n factorial. All right. And that's going to allow us to do some simplification, because I can now go ahead and divide out the n factorial. Now what am I left with? I'm left with the limit as n approaches infinity of n plus 1 squared over n, or n plus 1 over n squared, I should say, over or times 1 over n plus 1, because we divide out the n factorial. Now, we know what happens to this, right? If I divide everything by n, I guess I'll go ahead and write it. Let me go underneath that so I don't have to fight with that n over there. Right. So dividing everything by n, so that would give us 1 plus 1 over n over 1, right, times 1 over n plus 1. And as n goes to infinity, again, we know this is going to go to 1, right, because that goes to infinity, that goes to 0. And what's this going to do? Well, as n approaches infinity, 1 over n plus 1 is going to approach 0. Okay? So that's going to be 1 times 0, which is 0. Now again, that's the value of this limit of the absolute value of a sub n plus 1 over a sub n. So that was from our ratio test. So here's where I said, again, be careful of how you interpret. So what does the fact that that's 0 tell me? Well, it's a constant less than 1. And since it is a constant less than 1, then our series is absolutely convergent and therefore convergent. So I'm just going to say the sum of a sub n, our original series is absolutely convergent, therefore convergent. Okay? Yeah, so you have to be careful of the interpretation, right? What does it actually tell you? What have you found out by using the test? Because, like I said, remember when we talked about the ratio test, because this is the mistake I see all the time. The ratio test says that if the limit is equal to a constant less than 1, I have absolute convergence, greater than 1, I have divergence, equals 1, it's inconclusive. That limit comparison test that we talked about previously back in section 11.4 says that if I look at the limit as n approaches infinity of the ratio of a sub n to b sub n, and we take the series that we're comparing it to, and if that limit is equal to a positive constant, then either both series were convergent or both series were divergent, right? Tells us something completely different than what we have with the ratio test, but I inevitably see those two confused as far as what the result tells you, right? So we have to keep them separate. They're two completely different tests in how we set them up and in what you are using them to determine. All right, so be careful there. Can't emphasize that enough. I just see way too many mistakes. Now that third case, just to show you, we say, okay, well, if the limit is equal to 1, it's inconclusive. Here's a quick example as far as why. So this is at part 3 of the ratio test. If we look at the sum of 1 over n squared, right? That's a convergent p-series. That's 1 over n to the p, where p equals 2, right? We already know that's convergent. But if we use the ratio test, right, it's okay, let's test it for absolute convergence, which says I look at the limit as n approaches infinity of a sub n plus 1 over a sub n. So it would be 1 over n plus 1 squared over 1 over n squared, or n squared over n plus 1 squared, right, which is exactly what we had in the previous. So there's n over n plus 1 squared here, which equals 1. Right. Okay, whoop-de-doo, I get 1. We already knew the series was convergent, though, before we even started. Let's look at the sum of 1 over n, which, again, we already know what that series does. That's our harmonic series, right? That's our p-series with p equals 1. We called it the harmonic series, but we already know that that's a divergent series. Right? But if I use the ratio test to determine absolute convergence, because, again, absolute convergence and convergence are two different things, I want to know absolute convergence. So the limit as n approaches infinity, absolute value of a sub n plus 1 over a sub n would be the limit as n approaches infinity of 1 over n plus 1 over 1 over n, or then n over n plus 1 multiplied by the reciprocal. But again, dividing everything by n, we know that this would equal 1. Right? So the value of the limit in both of those cases is 1, but in the first case, we have a convergent p-series. In the second case, we have a divergent p-series, or the harmonic series, right? So there's a simple example. I mean, I get 1 in both cases, but in one case we're convergent, in the other case we're divergent. So that tells me that this ratio test, it can't be used to determine convergence or divergence if the limit is equal to 1. Right? It's inconclusive. So then you have to use a different test. You have to find another way to make that observation. Right? Now that's the ratio test. The root test, I tell you, it's not going to be a big player. It's one that, just simply because you don't see a lot of functions that fit the format to use it, but I'll show you how it works. It's very similar to the ratio test in that it deals with absolute value to determine absolute convergence. But it's when you have a function a series involving nth powers, right? Or if I have an expression raised to the nth power, not just a constant, because if I had a constant to the nth power, I could use geometric series. But if I have an expression, a function of n, let's say, to the nth power, this root test comes into play. Now, it's very similar to the ratio test in what it says, in that if I look at the limit as n approaches infinity of the nth root of the absolute value of a sub n, if it's equal to a constant less than 1, then the series is absolutely convergent and therefore convergent. If that limit is equal to a constant greater than 1, then the series is divergent. And if that limit is equal to 1, then again, it's inconclusive, just like the ratio test. So here's a quick example with that. Maybe one or two of these in your homework, not a lot. So let's consider the sum as n goes from 2 to infinity of negative 2 to the n over n plus 1 raised to the 5n power. So this is what I was talking about in that we have this quote-unquote function of n raised to an nth power, right? So using the root test, we're simply going to take the nth root of the absolute value of our series. Now again, I can drop the negative because of the absolute value, so I don't need that negative in front of the 2 anymore. So I'm looking at the nth root of 2n over n plus 1 raised to the 5n power. And that's, again, the reason we use it with these nth powers is because I've got this nth root and this nth of the nth power, right? Those are just going to cancel each other out, right? The square of the square root, or the square root of the square, vice versa. And so that leaves me with 2n over n plus 1 to the 5th. And now we can deal with that normally. Right? So I'll just divide everything by n. I get 2 over 1 plus 1 over n to the 5th. And as n approaches infinity, 1 over n goes to 0. So I'm left with 2 over 1 or 2 to the 5th, which is 32. That's the value of the limit. That's greater than 1. And this is, like I said, just like with ratio test, since the limit is equal to a constant greater than 1, then we say that the series is divergent. Okay? But again, root test is not a big player, but you will see one or two of those in your homework. So we do at least want to recognize when something like that can be used. But primarily it's ratio test. Ratio test used to determine absolute convergence. And if you have absolute convergence, you also have convergence. And that is section 11.6.